This lesson is from Chapter 11, Sections 5 through 7, and it's about colligative properties. Recall that colligative properties are things you can measure or observe that depend only on the number of particles in the solution, not on the identity of the chemical. The colligative property we've learned about so far is freezing point depression, where particles of a solute get in the way of particles of a solvent being able to attract each other and freeze. So it has to get even colder and have less motion before those particles are able to freeze. The math equation we use for freezing point depression is that the freezing point depression is equal to I kf m. I is the number of particles that form when you dissolve 1 mole of a solute, kf is the freezing point depression constant for the solvent, and m is the molality. Section 5 is about our second colligative property, boiling point elevation. There's usually a certain vapor pressure from molecules on the surface of a liquid turning into a vapor. However, if we add a solute and make a solution, then just like before, solute particles will block some of the solvent particles from being able to escape. So the vapor pressure will be lowered, and you'll have to get it hotter before the vapor pressure can increase enough to equal the pressure over the liquid, usually atmospheric pressure, and then it will boil at a higher temperature. The math equation we'll use for boiling point elevation looks just the same, except for the constant is different. It's the boiling point elevation constant. For water, the boiling point elevation constant is equal to 0.51 degrees Celsius times kilograms per mol. For example, 18 grams of glucose is added to 150 grams of water. The solution has a boiling point of 100.34 degrees Celsius. Calculate the molar mass of the glucose. I know the math equation is the same as for freezing point depression, except for with the boiling point elevation constant. I know my boiling point elevation is 0.34 degrees Celsius because water normally boils at 100 degrees Celsius. So the final is 100.34 and the initial is 100. Final minus initial is 0.34 degrees Celsius. Glucose has a funny name, so I know it's covalent, so I is 1. I know that Kb is a constant. It's always 0.51 degrees Celsius kilogram per mole. And the molality is not given to me, and I can't figure it out because I don't have the molar mass. That's what I'm trying to find. So we'll leave that molality. When I solve for molality by dividing both sides by 0.51, find out the molality is 0.67 moles per kilogram. At this point, we should ask ourselves, do I know how to find the molar mass, which is the goal of the problem? I know that molar mass has units of grams of glucose over moles of glucose, and I can find my moles from molality, and I'm given my grams in the problem. So I can just look at the units, moles and kilograms, and see that I would need to multiply by kilograms of the solvent to get moles of the solute of the glucose. Or if I need to, I can use the equation and know that the molality is moles of solute over 0.150 kilograms of water. So I can solve that by multiplying by 0.150 kilograms on each side of the equation. When I solve for moles of solute by multiplying 0.67 times 0.150, find out that I have 0.10 moles of glucose. Then I know that I have 18.00 grams of glucose. So 18.00 grams divided by 0.10 moles is my molar mass of glucose, which is 180 grams per mole. Our next section, section 6, is about osmotic pressure. Osmosis is the flow of a solvent into solution through a semi-permeable membrane. In other words, a filter that is porous or permeable or allows through some things but not others. The membrane in this case allows the solvent through, but not solute molecules to get through. Let's take, for example, the screen door on your house is a semi-permeable membrane. Here's your door, here's the screen, here's you. You are not smiling, you are a little bit scared because There is a very large vicious spider on your screen door. Now the spider is like a solute particle, and if the wind blows this away, it is partially blocked by the spider, and not as much wind can get through. If the wind blows this away, more wind can get through because the spider would get blown off the door. So the net flow would be towards the spider. Another example is when you make pickles. You take a cucumber, which has water inside it, and you put it into a solution that is more concentrated than the inside of the cucumber. Cucumber, of course, isn't just water, it's a solution, but it has a lot of water in it. When you put the pickle in a concentrated salt solution called brine, then the salt, these red dots, the solute, is kind of like the spider on your screen door, and the skin of the cucumber is kind of like the screen door, the semi-permeable membrane. The water can flow in or out of the pickle or the cucumber, but the salt can't. So there's going to be a net flow out of the pickle, and then it'll shrivel into a pickle instead of being a cucumber anymore, because the salt particles are blocking water that's trying to flow in. So the osmotic pressure flows from the less concentrated solution towards the more concentrated solution, and the pickle shrivels. Yes, it does. The math equation that we use is pi, which is osmotic pressure, is equal to I, which is the Van't Hoff factor, the number of particles that form when you dissolve 1 mole of solute, times big M, molarity, R, which is the ideal gas constant, is the one with pressure units in it. So it's 0.0821 atmospheres times liters over moles Kelvin, and temperature in Kelvin. So you can see that the higher the concentration is, the greater the osmotic pressure. And that's what makes it a colligative property. It depends on the concentration, the number of particles, not on what you're dissolving. For example, let's calculate the molar mass of beta-carotene if 10.0 milliliters of solution containing 7.68 milligrams of solute has an osmotic pressure of 26.57 millimeters of mercury at 25.0 degrees Celsius. The math equation that we're going to use is osmotic pressure is I times the molarity times the gas constant times the temperature. I'm going to convert my osmotic pressure to atmospheres because R has units of atmospheres. I is again going to be 1 because beta-carotene has a weird name, that means it's covalent. M is the molarity, and I don't know what that is because I don't have the molar mass of beta-carotene. R is 0.0821 attomoles. And then finally my temperature has to be in Kelvin because the units of R. So that's going to be 298 Kelvin. When I solve for molarity by dividing both sides by 0.0821 and 298, I find out that the molarity is 1.429 times 10 to the negative third moles per liter. As in the previous problems, I know the equation for molarity, so I know that the molarity is equal to moles over liters of solution, which is 0.01 liters. So if I multiply both sides by 0.01, I can find the moles of the solute. I can find the moles of the beta-carotene is 1.429 times 10 to the negative fifth moles. So then I know that molar mass is grams per mole, so I take my grams of the solute, which is 0.00768 grams, and I divide it by the moles I just found, which is 1.429 times 10 to the negative fifth moles, and I find out that the molar mass is 537 grams per mole. Our last section for today is section 7 of chapter 11. It's about colligative properties of electrolyte solutions. Up till this section, we've been saying that I is equal to 1, and we've been dealing with covalent compounds like glucose and sugar. In this section, we'll have I be more than 1. For example, I for NaCl. What would you expect I for NaCl to be? Well, sodium chloride breaks apart into 1 sodium and 1 chloride when it dissolves in water, so you would expect it to be 2. And so you can certainly use that for problems, but you're also expected to know that in real life, it's not really 2. When we measure I experimentally, we find out that it's not quite 2, it's a little bit less than 2. In a 0.01 mole solution, I is 1.97, which is very close to the expected value of 2. But in a 0.1 mole solution, I is only 1.87, which is less close than we would expect. This is because of something called ion pairing. Sodium and chloride ions are generally broken apart and separated by water because water is polar and it surrounds it and its particle motion breaks it apart. But you have to remember, sodium is still positive and chlorine is still negative, so the more concentrated it is, the more pushed together they are. Sometimes they do pair up enough so they don't act as 2 particles anymore and just act as 1 particle. Our last example of the day asks what concentration of sodium chloride in water produces an osmotic pressure of 7.7 atmospheres at 25 degrees Celsius. As soon as I see the words osmotic pressure, I know that my math equation is osmotic pressure, pi, is equal to I times molarity times R times T. The osmotic pressure is 7.7 atmospheres. I is 2 for sodium chloride. M, the molarity, we don't know. 0.0821 is the gas constant with units of pressure in it. And temperature in Kelvin is 273 plus 25, so that's 298. When I solve for molarity, I find out that my molarity is 0.157 molar, not what it says on the screen. In life, would you expect the osmotic pressure to be equal to 0.157, or greater than that, or less than that? And you should say that in real life, the osmotic pressure would be less because I would be less than 2 because of ion pairing. So today we've talked about colligative properties. We had already learned about freezing point depression, and then we talked about boiling point elevation and osmotic pressure. You should be able to list them, explain how they work, use their equations and calculations, and give practical uses for them.